CRC mechanism, cyclic redundancy check. This is the method is being used in communications. Cyclic redundancy check is the method used in communications because this is going to detect either error can be single or multiple. Whether the number of errors are even or odd, still it is detectable by this. Okay. So here is something new procedure is being used in this. So what that is, suppose I want to send a data which we are going to call as a message polynomial. Which we are going to call as m of x. We will be using another called generator polynomial. Which is g of x. Okay. Message polynomial m of x. So this is m of x. Okay. And this is divisor is the g of x. Now what we'll do is we'll divide the message with the g of x. So whatever reminder we are going to use as CRC character, cyclic redundancy check character. So we will append this CRC character to the data. Okay. So actually speaking, it is shown like this: data on LSB side, CRC. Then at the receiver, this data with CRC is again divided with the same generator polynomial. So now this is being taken as m of x, and this is being taken as g of x. After dividing whatever reminder, if the reminder is 0, no error. If reminder is not equal to 0, error. So depending on the number of errors, the value of reminder is different, but non-zero. So this is the concept used in this. But originally what is being done is, depending on the degree of g of x, based on the degree of the g of x, so the original data is appended with so many zeros on the LSB side, which is equal to degree of generator point. Then that is being, this entire is being divided with g of x, and whatever remainder we are going to get, the number of bits in the remainder is equal to the degree. That is being added, appended on the LSB side. That is being transmitted. So receiver will receive the same. Again, receiver will divide the received information with the generator polynomial, and receiver will observe the remainder. If the remainder is 0, whatever received is correct. Now, based on the degree of the generator polynomial, those many bits on LSB side will be discarded, and remaining data will be accepted and processed if remainder is 0. If remainder is non-zero, this entire will be discarded, and receiver will ask for the retransmission by sending a negative acknowledgement. So this is what is being done in CRC mechanism. Okay. CRC mechanism, this is what is being done. So we'll see an example for this also. Okay. So if you see this particular case, now in this particular example, suppose I'm using a 4-bit data. This is m of x. Okay. and I am using 4-bit divisor. This is g of x. So here the degree is the number of bits n minus 1. So here the number of bits are 4 minus 1. So degree is 3. Degree of g of x is 3. As a result, what I am going to use, I am going to append 3 zeros on LSB side of my message m of x. So now this entire will be divided with the g of x. So whatever remainder I am going to have, remainder is number of bits in the remainder is equal to degree of g of x. So now this entire thing will be transmitted to the receiver. Then receiver will receive my original information plus the remainder. So the entire thing is again divided with the same g of x. And the remainder what we are going to get, if that is equal to 0, whatever received is having no errors, that will be accepted and forwarded, stored for further processing. If the remainder is equal to non-zero, then whatever is received is wrong, that is being discarded. Okay, and ask for retransmission. So this is what is going to happen. Okay, now in this, the message can be represented either, say, for example, if this is the message we want to send, okay, 10110. The same thing can be represented with x power 4 plus x square plus x. So generally this LSB is 1 plus 1. Okay, suppose if I want to send 10111. So this can be same represented either an algebraic expression or in terms of binary bit stream. Okay, so 1 indicates, see, power 0, 1, 2, 3, 4. So power 4, so x power 4. Power 3 is 0, so that is absent. Power 2 is 1, so x square. Power 1 is 1, so x. Power 0 is 1, so 1. So this is how we can represent message information either in the bit stream in binary or an algebraic expression. Similarly, the generator polynomial, suppose g of x I want to use as, say, 1011, for example. Now, this can be specified as x power 3, x power 2 is 0, plus x power 1 is there, plus 1. Okay. So this message polynomial and generator polynomial, they can be shown either in terms of binary bit stream or in terms of algebraic expression like this. Now in this case, the generator polynomial is this. Now its degree is 3. Okay, degree is 3. And if it is represented binary bit stream, 4 bits, like D3, D2, D1, D0. So degree is 3n minus 1. If the generator polynomial is represented in terms of binary bit stream, then the bit stream is having n bits. Degree will be n minus 1. If it is expressed in terms of algebraic expression, then the highest degree, highest power will be the degree of the generator polynomial. So based on this, so we can able to identify the message and generator polynomials, and we can perform the division at the sender. Same thing will be verified at the receiver place. Okay, so we'll see with an example for this. Hope everyone is understanding till now. Okay, now at this point, we'll see. Suppose I want to send the m of x is say 10101. Okay. And I may be using a generator polynomial 1101. Okay. So the number of bits n is equal to 4. Then degree will be 3. We have to see only the bits of the generator polynomial, not the message. Please remember this point. Okay. So everyone should remember this point. Now as the degree is 3, now the message is 10101 and degree is 3. So append 3 zeros on the LSB side. Now this is what we have to divide with 1101. So in this division, what we are doing generally subtraction, but in this particular case, we'll be doing the XOR operation. So if the MSB is 1, so we can say 1101. We are not bothered about the partial product, partial dividend is greater than the divisor or not. We are not bothered. But what we have to make sure is MSB must be 1. Okay, as MSB of divisor is 1. So dividend MSB should be 1. Then without any problem, we can perform the division. Okay, here the division is nothing but modulo division or XOR operation. 0 and 1 is 1. 1 0 is 1. 0 1 is 1. Okay, 1 1 is 0. So this is being ignored. Now 3 bits are there. So 4th bit we are going to get it. Again MSB is 1. So again 1101. Okay. Next 1 1 is 0. 1 0 is 1. 1 1 is 0. 1 1 is 0. This 0 ignored. Now this 0 will be appended. Now MSB is 0. So we cannot. So 0 times. See, the quotient is not important. We are not bothered about. Okay. We are important with the remainder, not the quotient. So 0 0 XOR operation is 0. 0 0 is 0. 0 1 is 1. 0 0 0. 0 is ignored. Next 0 will be appended. Now MSB is 1. So 1 1 0 1. Okay. Now perform. 0 1 XOR is 1. 0 0 is 0. 0 1 is 1. 1 1 is 0. Ignore. The final bit is appended. Now MSB is 1 again. So 1 1 0 1. Okay. Now this 0 1 is 1. 1 0 is 1. 0 1 is 1. 0 0 is 0. 1 1 is 0. Sorry. So this 0 is ignore. So now no more bits to append. So this is the remainder. Okay. This is the remainder. Now what is this remainder is to be replaced with these 3 bits. That means the message to be transmitted. Message to be transmitted is so 1 0 1 0 1 and instead of three zeros 3 ones we have to append. So this is the information to be transmitted. Okay. This is the information to be transmitted. Suppose this information is received as it is. Let us assume that this 1 0 1 0 1 1 1 1 is received as it is, no errors. So 1 1 0 1. So MSB is 1 1 0 1. Okay. This is what we are doing at receiver side. Okay, this is what we have done at the sender side, transmitter side. And this will be doing at the receiver side. So 0 1 XOR is 1. 1 0 is 1. 0 1 is 1. So 1 1 is 0. Ignore this. Now this bit will be coming into this position. Okay. Again, MSB is 1. So 1, 1, 0, 1. 1, 1 is 0. 1, 0 is 1. 1, 1 is 0. 1, 1 is 0. So this 0 is ignored. Now this bit is being appended to this. So MSB is 0. So 0 times 1, 0 is 1. 0, 0 is 0. 1, 0 is 1. 0, 0 is 0. Ignore this. Now this bit. Okay. Next MSB is 1. So 1, 1, 0, 1. 1, 1 is 0. 1, 0 is 1. 0, 1 is 1. 1, 1 is 0. Ignore this. The final bit 1. Okay. Next, the divisor is 1, 1, 0, 1. So 1, 1 is 0. 0, 0 is 0. 1, 1 is 0. 1, 1 is 0. Ignore this. So the final remainder, no more bits are there to append. So final remainder is 0. That means no errors. So whatever is received is no errors. Out of this received, so LSB 3 bits are discarded. This is the original message that is being accepted. Okay. So here what is to be done? So the same generator polynomial, both sender and receiver should use. They have to agree for that. Okay. So now our original message to be received is 1, 0, 1, 0, 1, 1, 1, 1. This is the original message to be received. Let us take some error is there. Okay. Suppose this 1 is not received correctly. Say that maybe say 0. This 1 is also 0, 0, 1, 1, 1, 1. Okay. So this is wrongly received 0. Let us see 1, 1, 0, 1. So 1, 0, 0, 0. 1, 1, 1, 1. So 1, 1, 0, 1. 0, 1 is 1. 0, 0 is 0. 0, 1 is 1. 0, 1, 1 is 0. Ignore this. Get the first number. Okay. MSB is 1. So 1, 1, 0, 1. 1, 1 is 0. 1, 0 is 1. 0, 1 is 1. 1, 1 is 0. Ignore this. Get the next bit. Okay. So MSB is 1. 1, 1, 0, 1. Next, 1, 1 is 0. 0, 0 is 0. 1, 1 is 0. 1, 1 is 0. Ignore this. Get the next bit. Okay. MSB is 0. So 0 times. 1, 0 is 1. 0, 0 is 0. 0, 0 is 0. 0, 0 is 0. Ignore this. They get the final bit. Again, MSB is 0. So 0 times. 1, 1, 1, 0 is 1. 1, 0 is 1. 0, 0 is 0. 0, 0 is 0. Ignore this. No more bits to append. So reminder what we are getting is 0, 1, 1, which is non-zero. So error. It is saying only one error, but where is the error? Not. Okay. That is the CRC mechanism. This is being used because if the error bits are being changing the positions, the remainder values will change. That is why almost every error will be detected, whether it is single error or 2 errors or 3 errors or n errors, irrespective of the number of errors, the errors are being detected. So that is why this is the mechanism preferred everywhere in the communication now, CRC mechanism. Okay, but what we need to remember is both sender and receiver should be agree the same generator polynomial. Suppose I want to communicate, suppose A and B want to communicate, then both A and B should use a generator polynomial say G1x. If A want to communicate with C, then both can use some other generator polynomial G2X. Everyone need not use. A pair can use a particular generator polynomial. Other pair can use a different generator polynomial. Likewise, as and when A is communicating with B, they will use G1X. As and when A is communicating with C, G2X. Suppose if B want to communicate with C, they may be using a third generator polynomial. Okay, likewise. So every sender and receiver, a particular sender and a particular receiver will use a particular generator polynomial between them, like what we have seen in this. This is a mandate. Okay, so that is about the CRC mechanism. Hope everyone has understood. Okay, hope everyone has understood. And one more is, this is the same example is shown, examples are being shown in this. So this is the data 1001 message, generated polynomial 1011. Okay, so number of bits in the generator are 4, degree will be 3, so 3 bits are appended after performing the division. So reminder what is got is 110. So 110 is appended with the original message 1001. So this is the information to be transmitted. And receiver will receive that 1001 with 110 as the reminder. Now this entire is being divided with the same generator polynomial at the receiver side, 1011. Okay, after performing the division, so final reminder is 0. That means no error. Whatever information received is correct. So the original information part 1001 is accepted. Suppose this 1 is received as 0. Instead of 10 is received at this point, there is error. Now this received 1 is being divided with the same generator polynomial. And finally, what we are getting is a non-zero reminder. A non-zero reminder. So that indicates there is an error in the received information. So this will be discarded, will not be accepted. So this is how the error checking mechanism is being used.